fundamentally, when we're talking about trig, it all comes down to the relationships between sides of triangles. So I'm going to draw a triangle here. And specifically, I'm going to put a right angle notation in there because mine doesn't look like it's got a right angle, but that thing is a 90-degree angle. And that guy right there is theta. And theta is usually the letter that we use as a fill-in for some angle. Based on the way that I have drawn in where that angle is, sometimes we label the sides of this triangle as the adjacent, the opposite, and the hypotenuse. Personally, most of the time I prefer to think of these sides as actually being X, Y, and R. Either way we're looking at it, our trig functions are all ratios of the sides of a right triangle. Fundamentally, that's what our trig functions represent. So if I write sine theta, and I would read this as sine of theta, the ratio that that represents is the opposite side over the hypotenuse. If I had cosine of theta, that represents the adjacent side over the hypotenuse, whatever that ratio is as a number. And tangent of theta is the opposite over the adjacent. I told you, I'm dialing it way back. People, like there's a phrase that sometimes we use to remember all this stuff. Anybody know the phrase I'm talking about? Totally. SOHCAHTOA. So however you want to write that. SOHCAHTOA. SOHCAHTOA. Or SOHCAHTOA. However you want to think about it. It's a useful memorization technique. It doesn't actually mean a whole lot. It's just there to help you memorize how things connect together on the sides of a triangle. We also have the inverse, sorry, poor choice. We also have the reciprocal functions for each of these. So if I wanted to talk about the hypotenuse over the opposite side, then our reciprocal functions look like, my pen will start writing in a second here. They don't like the cold mornings, okay. So 1 over sine theta, which we also write as cosecant of theta, would be the hypotenuse over the opposite. And I read this as cosecant of theta. 1 over cosine is secant of theta. That's the hypotenuse over the adjacent. This guy is secant of theta. And 1 over tangent of theta is called cotangent of theta, and that's the adjacent over the opposite. Cotangent of theta. If that all looks like a list of stuff to memorize, it's because it is. This is a list of stuff to memorize. There's no like magic algebraing your way out of it. These relationships need to be memorized. These need to be memorized. I don't choose to memorize this part. I only choose to memorize this part. Because no matter what the problem is, if I've been asked something with cosecant, secant, or cotangent, I'm probably going to go back and move it into sines, cosines, and tangents to work with it. So I don't bother trying to memorize a whole nother set of which sides of a triangle we're talking about. Okay. Speaking of sides of triangles, there are a couple of special triangles that we kind of have to memorize relationships of sides for. So here's how I personally remember all those special angles. If you already have this stuff memorized from a previous life, don't unlearn things you already know. Roll with what you already know. If you already know all of this stuff in terms of degrees and the new piece is worrying about radians, get fast at converting degrees to radians, right? But don't unlearn skills you already have. Okay, so here's how I approach the special angles. There are really two shapes that are the most important. Now, we got to remember trig has been around a really long time. Trig is some of our, like trig and geometry. This is actually, even if they weren't called these things and by these names, the geometry part of this goes back centuries. This is at the heart of every construction project ever, right? And so if we think about like fundamental shapes, squares and equilateral triangles show up in a lot of ancient construction projects. Our pyramids, regardless of whether that's Southern Hemisphere in South America, whether that's in Africa, whether we're talking about in Asia, regardless, we've got a lot of structures with a square base. So just remember, geometry and trig are ancient shapes. We need squares and equilateral triangles to build pyramids. Yeah. Oh, got it. Yeah. So I've got this square. So all of the interior angles of that square are totally. So you can think about it as 90 degrees, or you can think about that as pi over 2. Your choice. For now, I'm going with degrees, and then we'll sprinkle on the radian stuff later. So all of these interior angles are 90 degrees. And because it's a square, if I told you this side was 1, this side is also 1. Because it's a square. And now I'm going to bisect it. I'm going to bisect the angles, meaning I'm going to cut it in half. But when I cut it in half, I took a 90-degree angle, and cutting it in half means that that's 45 degrees. Don't unlearn stuff. What's the other side of the triangle? Thinking about Pythagorean theorem. I will give you all 30 seconds to come up with the other side of the triangle. If you have it memorized, great. If you don't, Pythagorean theorem that. I'm looking at an A, a B, and a C. Put together some A squared plus B squared equals C squared to get that last side. I figured there's so much to memorize with trig. Oh, sorry, I'll make my phone on silent. I figured there's so much to memorize with trig. If there are some things we already know how to do, it's not worth memorizing new stuff for. Does anybody get an answer for side C? Sorry? Almost a 2? Square root of 2, because C squared would be equal to 2. Yeah. So square root of 2 on that side. Well, what that means in terms of our trig functions, I can now evaluate for a 45-degree angle what the ratios of the sides are. So I can think about sine of 45 degrees. I'm looking for the opposite side. By the way, the adjacent side is whichever one shares the angle with the hypotenuse. The hypotenuse is always the longest side of a right triangle. So it's usually depicted as kind of the slanty one. So sine of 45 degrees is going to be that opposite side over the hypotenuse. If you have memorized trig stuff from a previous life, this might not be the way you memorized it. You might have had a teacher that really insisted on rationalizing denominators, in which case you might have this memorized as square root of 2 over 2. It doesn't matter at all, even slightly, in calculus, which version of this you like. So I like 1 over square root of 2 because it comes directly from my picture. But root 2 over 2 is also a correct answer and usually the one you're going to see in the back of a textbook. Your teacher won't care. Or more importantly, your TA, who's the one actually grading your test, won't care. If I went to find cosine of 45 degrees, same deal. I'm looking at this time the adjacent side over the hypotenuse. So 1 over the square root of 2, or you could rearrange that to say square root of 2 over 2. If I think about tangent of 45 degrees, I'm going to get the opposite over the adjacent, or 1 over 1, which we just think of as a 1. Now there's something subtle in what we just did here, but if you walk away with only one thing today, it should be that the sine by itself doesn't mean anything. Sine is telling me, look for the ratio of the sides of a triangle, but I have to know what triangle to look at. And the only way to know what triangle to look like is to have an angle inside. So super, super dumb, really super dumb, but that says sine of X. That just says sin. That's a word in the dictionary. This is not math. This is just a word. That's a function because he has an argument. This is saying sine of something. There's an angle that belongs to it. Writing this isn't math. Okay. Moving on. Question. Oh, stretching. Stretching is good. Improves circulation, keeps you awake, all kinds of good stuff. Just to drive one other point about trig stuff home, don't even bother writing this on your paper, unless, I guess you could. But if I made my square bigger, someone pick a number, anything between 2 and 12. So if this were a 7 by 7 square, and I cut it in half, that would still be 45 degrees. I could still use Pythagorean Theorem to get this extra side. It's just going to be a little messier. But I would have 7 squared plus 7 squared is equal to c squared. I'm going to do it. 7, that's 49 plus 49. That's 2 times 49, which means that's the square root of 2 times 49 is equal to c. Yeah. So square root of 2 times 7 is equal to c. So 7 square root of 2. That's my last side. Trig functions only need to know the angle. Because as soon as a trig function knows the angle we're talking about, the ratio of the sides has to be the same. So when I come in here to find sine of 45 degrees, even though my square got bigger, the angle didn't change. My square got bigger, but if I take the opposite side over the hypotenuse, I still end up with 1 over the square root of 2. So the only thing that a trig function needs to know is what the angle is. Okay, more fun with our other friendly triangle. So I'm going to take another shape and cut it in half. So I had a square, and next I'm going to have an equilateral triangle. And on my equilateral triangle, because I'm going to cut it in half, I need an even number to work off of. Anyone have a favorite even number? Don't get too big because we have to do math with it. Yeah, even number, 8. Okay, so that's an equilateral triangle. And because it's an equilateral triangle, I know the interior angles are all 60 degrees. We're going to have sides of 8. And because it's an equilateral triangle, that means all of the sides are 8. But when I cut it in half, because this bottom whole side was 8, it means the half I'm looking at is only 4. And because I cut it in half, that 60-degree angle up here at the top is 30 degrees. And we can use Pythagorean Theorem once again to get the missing side of that triangle. It got a little messy in here, so I'm going to draw it again over here. But I know that my hypotenuse is 8, this side is 4, and if I'm not sure what that other side is, I can go 8 squared is equal to 4 squared plus b squared, and we'll just do some math. 8 squared is 64. 4 squared is 16. 64 minus 16 is 48. So I'm going to have the square root of 48 is equal to b. I don't have to simplify that, or I don't know, like simplify in quotes. I think that's a nice simplified answer. But another algebraically equivalent form of this would be to take that 48 and find perfect squares that might be hiding inside of it, right? So 48 is 4 times 12, or 3 times 16. So this is the square root of 3 times 16, which means square root of 16 is going to give me a 4. So I've got 4 square roots of 3 is what my b value is. So this height here is 4 square roots of 3. Well, now this triangle has 2 different angles that we can work on. I can work on the 60-degree angle or the 30-degree angle. I'm going to go with my 60-degree angle first. So I could ask, what is sine of 60 degrees? And for that 60-degree angle, my adjacent side is 4, and the opposite side is 4 square root 3. So opposite over hypotenuse for sine, I'm going to have 4 square roots of 3 divided by 8. And if we simplify those fractions, I'm looking at square root of 3 over 2. Again, if you have that value memorized from a previous life, don't unlearn it. You probably already know some of this. Don't unlearn it. If I wanted cosine of 60 degrees, I'm going to take that adjacent side over the hypotenuse. So I'll have 4 over 8 and get 1/2. And tangent of 60 degrees is the opposite over the adjacent. So 4 square roots of 3 over 4, or the square root of 3. Now I mentioned that we can also get all the 30-degree angle information from the same picture. kind of convenient. 2 for the price of 1. So now maybe we just like turn our head or turn the camera. I won't really do that. It's kind of nauseating. But you could turn your head, turn the camera. I'm just going to go ahead and kind of lay that triangle down on its side. So that was the 30 degrees. 4 is the side opposite of the 30 degrees. My hypotenuse was 8. And the adjacent side to the 30 degrees is 4 square root 3. So if you haven't already done so on your paper, go ahead and fill out what sine of 30 degrees is, cosine of 30 degrees, and tangent of 30 degrees. If you know these from memory, great. Just test yourself, write down the answers you know. If you don't know these from memory, practice using the triangle. How'd I do? Now, I'm just going to point out that because you all get a page of notes or a note card or whatever, if you're really feeling nervous about the trig, then have a backup plan and write some of this on that note card. Normally, I would tell you all of this needs to be memorized because normally you wouldn't get a page of notes in 16A. I don't know that you'll get a page of notes in 16B, right? I haven't looked. Is Babson teaching 16B in the winter? If he is, stick with him if it's going well. But you often would not get a page of notes, and it would be expected that you have those special angles memorized for trig stuff. Where to go next? We could go unit circle, converting stuff to radians, graphing stuff. Anyone have a preference? Question? Okay. What do you, okay. Well, yeah, that would just be like going over some problems on the homework. Yep, totally. I am planning to do some product and quotient rules. So just gonna roll through a little bit more trig. Okay. So yeah, let's roll into unit circle stuff. So watch me draw a circle, folks. Oh, that's not bad. I did pretty good. Okay. My recommendation is always to draw the circle first and then put your axes on. It's way easier to hit the middle of the circle that way. Much harder to line up your circle. Okay. Here's my, also if you use erasable pens, you can clean your circle up a little bit. Okay, there's my circle. The reason that we refer to things as the unit circle is because we talk about it having a radius of 1, and that's all it means to be a unit circle. I mentioned that I prefer to think of my triangles for trig stuff with an X, a Y, and an R. And that's because of how that falls onto our unit circle. So I mentioned before that all the geometry and trig stuff goes way, way back. Predates electricity. If it predates electricity, there are lots of aspects of your life that are ruled by the sun. So that's how I remember that for trig stuff, our angles are always in reference to the horizon, because they're always in reference to thinking about sunrise and sunset. So that means that if I were looking for an angle of 30 degrees, and this one, does anyone know who invented clocks? I don't know why our clocks don't start here and go this way, but that's what happens with our trig. So an angle of 0 degrees is right here. 90 degrees is up at the top. If I go another 90, I'm at 180 degrees. Another 90, I'm at 270 degrees. Another 90, I'm back to where I started at 360 degrees. For our angles, they move counterclockwise. Sure would have been nice if our clocks all started with a 1 here or something. I don't know, but they don't. So 30 degrees is here in the first quadrant. And if I draw the triangle in, the angle should always be the angle that that triangle makes with the x-axis. Because it's a unit circle, we usually write in that the radius is 1. The coordinates here would come from like an x and a y value. So let's think about what that means in relation to our trig functions. So I know something about this side. That x is my adjacent side, which means it's got something to do with a cosine. So for the triangle that I drew, if I wrote cosine of 30 degrees, that would look like my adjacent side over the hypotenuse, or just x. If I were looking at sine of 30 degrees, that would be my opposite over the hypotenuse, or y over 1, or just y. So when it comes to the unit circle, our x value is associated with cosine of that angle, and our y value is associated with sine of the angle. So if you were to look up a unit circle chart, or grab the one out of our textbook, they're often labeled with x and y coordinates that correspond to the cosine and sine values. So cosine of 30 degrees, hey, we just found that. Cosine of 30 degrees, that's square root of 3 over 2. Sine of 30 degrees, that's 1/2. So we usually label the points on a unit circle in that way, where the x coordinate is our cosine value, the y coordinate is our sine value. There are some special points that the unit circle helps us to deal with because we can't actually draw a triangle to get there. And that's all of these edges, the 0, the 90, the 180, and the 270. But if we think about all of those with our x and y coordinates, that's how we can sort of extract the sine, cosine, and tangent values. So over here at 180 degrees, that's got a coordinate of -1, 0. Well, that tells me that cosine of 180 degrees is equal to -1, and sine of 180 degrees is equal to 0. There's a special thing with tangent that I didn't mention at the beginning, but now's a good time. Since tangent of an angle is the opposite over the adjacent, if we think about how I've defined things on the unit circle, that means that tangent would be the y value over the x value. And our y value came from sine, and our x value came from cosine. So tangent of theta is equal to sine over cosine. And that's going to be important for us. Or in this context, if I wanted to find tangent of 180 degrees, that means that I would be looking for 0 divided by -1, which is 0. Good times. And we can do the same thing looking at the coordinates for 0, 90, 180, 270. But I do want to switch gears and talk radians for a second. So the people that invented calculus, and yes, calculus was invented. Calculus was invented as a way for physicists to put equations to the things that they were observing. So calculus was invented, and the people that invented calculus, they were like, wait, we shouldn't have to have things that rely on, if we're talking about something moving around a circle, we don't want calculus to rely on the size of that circle. We want calculus to be independent of the size of the circle. So they decided to scale everything by the radius of the circle. And that's how we end up with radians. Question, answers. Absolutely, excellent question. If I tried to find cotangent, not cosine, cosine's good, cosine's friendly. If I try to find cotangent of 180 degrees, we would get -1 over 0. So we just say that it's undefined. Yeah. Okay. Onward to radians. So anyway, these mathematician physicist folks, they said, well, if I move all the way around the circle, then what's the distance around the circle? It's also known as the circumference, or 2 pi times the radius. We're going to call that 2 pi radians. That's the full distance around the circle. So now when we think about the unit circle, we're still going to start in the same place. So that's going to be 0. But when we travel all the way around, we end up at 2 pi. That means that if we only traveled halfway around, we're at pi. If we only traveled a quarter of the way around, we're at pi over 2. And if we traveled 3/4 of the way around, we're at 3 pi over 2. And all of our angles in between, we can think about as fractions of a full circle, or fractions of the circumference. So we can either think about them by breaking this up, or we can think about them from a straight conversion perspective. So if I'm going straight up conversion, then if I had 60 degrees and I want to convert it to radians, think like chemistry, stoichiometry, or unit conversions or something. I need the degrees to go away. So I need 2 equivalent things. Well, 2 pi is a full trip around the circle, and a full trip around the circle is 360 degrees. So I can think about this as 2 pi divided by 360, because the 2 pi and 360 are equivalent measures. Or I really prefer to think about it as pi over 180, just so my numbers are a little bit smaller. Because halfway around the circle is pi radians, or 180 degrees. That means that is a pi over 3. So like the complete list of nice angles that we're supposed to know some stuff about. I'll go degrees and radians. We should know about 0. We should know about, oh, sorry, I'm putting that in the wrong column. Pi over 6. Well, pi over 6, that's just half of the 60 degrees we just found. So that's 30 degrees. 45 degrees, that's pi over 4. 60 degrees, that's pi over 3. 90 degrees, that's pi over 2. And then we talk about all of those same angles, but existing in each of our 4 quadrants. I don't need to get too deep in the weeds here, but there's a little phrase that sometimes people think of. All students take calculus or another stupid trig class, whatever fits better for you in this moment. That's a way of remembering which of the trig functions is positive in each of the quadrants. I choose to think about it as if cosine goes with my x values, then my x values are positive in quadrants 1 and 4. If sine goes with my y values are positive in quadrants 1 and 2. So I kind of think about it relative to the x's and y's rather than this, but that'll totally work. Okay. Is that like enough of a trig interlude? We can go back to doing some calculus-y stuff. Let's say I had a function that looked like 3x squared plus 4x over x cubed minus 2. Well, one technique that we might try first is like the section of the book where you try to do some algebra to it to rewrite it before we take a derivative. But there's no algebra I'm going to do here because of the denominator. So instead, I step back, I look at the overall thing, and I say, oh, I have division. So I'm going to think about it as that whole top piece is my f, and the whole bottom piece is my g. So when I apply the quotient rule to this, y prime, I'm going to leave myself spaced for the derivative of f times g minus f times the derivative of g all over g squared. I like to have all my pieces set up first. Well, the bottom I don't have to do any calculus to. And the numerator has 2 pieces I don't have to do any calculus to. Then I sprinkle on the calculus. So the derivative of the top here looks like 6x plus a 4. And the derivative of the bottom looks like 3x squared. And then I would walk away and not try to simplify anything at all. Now I know there was a specific homework question, maybe, that someone wanted to go over, but I don't know whether it was specific or general. Should I just go for a couple more practice problems? Okay. So the truth is that our product and quotient rule become much more interesting once we have other types of functions in the mix, like trig functions. So I'm going to do one more example here, and then I'm going to have some more fun with trig. But there's a set of questions in the book that I find kind of confusing, and they look kind of like this. Suppose that I told you that f of 2 is equal to 4, f prime of 2 is equal to 1, g of 2 is equal to 7 and g prime of 2 is equal to -3. And then I asked you to find the slope at x equals 2 of y equals f of x divided by g of x. Well, that looks kind of gross. And I didn't actually give us the functions f of x or g of x. I did, however, give us all of the information that we need in order to apply the quotient rule. So this is sort of a way that I can like put a twist on a quotient rule problem, because this is more testing your understanding of the formula and like the big picture idea of quotient rule and less testing your calculusiness. So if I'm going to find the slope at x equals 2, well, how do we find the slope of a curve? It's kind of our default answer for 16a. We got to take a derivative. So if I'm going to take the derivative, we're looking for like, what is y prime evaluated at 2? My function is a quotient, which means if I just think about quotient rule, that needs to be f prime g minus fg prime all over g squared. But I'm applying it at the particular point of x is equal to 2. So all of these pieces become their particular value at 2. And then we're plugging in all the numbers. So f prime of 2, looking at my list, f prime of 2 was equal to 1. G of 2 was 7. F of 2 was 4. G prime of 2 was -3. And G of 2 was 7, so the bottom will be 7 squared. So I could simplify that a little bit. That's 7 minus a negative, so that's like 7 plus 12 over 49, or 7 and 12 was that 19 over 49. And that would be my slope at x equals 2. I could also ask us to find the equation of the tangent line. So maybe like part A was find the slope and part B is to write the equation of the tangent line. Okay, we did most of the work. So I'll just give you a minute on your paper to write down the equation of the tangent line. You don't have to like rearrange it or anything. Just put the pieces in where they go. Also, I was definitely about to try to drink through my mask. That was not going to end well. I looked at this section of the book and I really thought this was the most confusing type of question in there. But if there's another type of question in that section of the book that someone wanted to go through, we can take a look at that as well. So to write the equation of a tangent line, I know that I always need a point and a slope. We just figured out our slope. And in terms of our point, I know that x equals 2 and y should be f of 2 over g of 2. So that would be 1/7. So if I were writing the equation of the tangent line, I would just write it as y minus 1/7 is equal to 19 over 49 times x minus 2. You could do y equals mx plus b. Question? So that's because that's how I defined the y value. Yeah, like that wasn't some sort of magic. That's just for this particular question, how I defined y. Yeah. Oh, I don't know. Thank you. 4/7? 4/7. Now it is. More questions. That's okay.
So I just wanted for a form of which I have.
Sure.
I think I understand how far I need to go. Like if I, where can I leave it and when should I like?
Oh yeah. So I will say that knowing when to walk away and when to keep trying to simplify, there's some subtlety there that usually depends on the context of where I'm doing it. If I'm trying to check my answer with the back of the book, I'm going to have to do quite a bit of simplifying in general. If I'm doing a homework problem, I'm probably going to take the time to do that work because it's good practice in terms of the algebra stuff. If it were a quiz or a midterm, I usually just quit and walk away unless there's another step to the problem that would be beneficial if I were to simplify. So what do you have for me? Did I get it right? Okay. So if I'm looking for the derivative here, first of all, two options. We could do this like we did in the previous section where I FOIL that out first and then take the derivative. But if we want to practice the chain rule, if we want to practice the product rule here, then I've got two pieces. I've got the f and the g. So I'm going to take the derivative of the first piece times the second plus the first piece left alone times the derivative of the second. And then I'm going to quit. Yep. I'm for sure going to quit there. Now, if the question that you were asked, for example, was, where does g of x have horizontal tangent lines? Well, now I got to do something with that. So what's the slope of a horizontal line as a number? Yes, silence or 0. Yes, it's always 0. So this is really asking us, where is g prime of x equal to 0? So now I'm going to look at that and think about, oh, I'm going to have to do some work on this. I can choose what kind of work to do, right? Maybe I can try to factor it, but I'm looking at these two pieces. The only common factor really is 2. So I would probably be distributing this stuff out to answer this question. Since I wrote it, I might as well finish answering the question. So if I do this and distribute everything out, 2x times 2x, that's a 4x squared. 2x times 5, that's 10x. This 2 would get distributed in, so I'd have plus 2x squared and plus 2. Putting that together, I've got 6x squared plus 10x plus 2. I can factor a 2 out. I don't think that factors. Clearly, this would be a terrible question to get asked. But what do you do if it doesn't factor? We got skills. What's our next best option if that doesn't factor? cry is not an option. Yeah, I'd probably go for quadratic formula. Some people like to complete the square. I'm not one of them. So I would probably reach for quadratic formula at that point and say, okay, well, x is equal to -5 plus or minus the square root of 5 squared minus 4 times 3 times 1 all over 2 times 3. And definitely quit there. Okay. Let's venture back into trig land so that we can practice some more product and quotient rule with interesting functions. So if I venture back into trig land briefly, be brave. Sketch a graph on your paper of sine of x. It doesn't have to be big. It doesn't have to be pretty. You could just squiggle it with your eraser, leaving a little eraser trail if you're not super confident. But basically, what does sine of x look like? I see some finger waving. Finger waving works for me. Something that squiggles, some sort of squiggly thing. Let's get slightly more specific on our squiggles. So sine of x, and remember, I read this as sine of x because trig functions have to have an angle. They've got to have an argument in there. Otherwise, they don't know what they're looking at. So sine of x looks kind of like this. Now, I have drawn one period of sine of x, but if we think back to our unit circleness, I can keep going around and around in circles. And sine of x, as I move around and around in circles, it's recording what's my height. So if I think about moving around this circle, I start at a height of 0. I get up to a height of 1 when my angle is pi over 2. So in terms of this graph, because sine corresponds with my y values, I started at a height of 0 and we get up to a height of 1 at pi over 2. Continuing to go around the circle, I'm at a height of 0. I get to a height of +1. I come down to a height of 0 again. And then I go to a height of -1 and back up to a height of 0. So on my sine graph, that means I'm at 0 at pi. I'm at -1 at 3 pi over 2. And we kind of finish up here at 2 pi. But technically this thing keeps going. So like out there on the edges, I can think of this continuing to do that forever and also in the other direction. Each time that sine completes one full revolution of going like a height of 0, up to 1, down to 0, down to -1, back to 0, we call that one period. Which for a regular old sine graph is 2 pi radians. But I'm about to challenge our senses. And to do that, I think I need a simplified and maybe larger graph. Yeah, let's go for it. If you drew yours big enough the first time, don't worry about doing it again. Here's my plan. That's my sine graph. How do you find the slope of a tangent line? We're going to practice saying it together. And even if you're at home or somewhere else, if you're in a quiet space and it won't look too weird if you're on Zoom, you can say it out loud or you can mouth it. Inside of your mask, no one will even know. Find the slope of the tangent line. We're going to take the, pretend everyone said derivative really loud. Okay. That means that I'm going to take the derivative by finding the slopes of the tangent lines. Cool. For this picture, for like the portion of the sine graph I drew, how many places are you 100% sure you know what the slope is? Just this little portion I drew. Just the little guy at the bottom. Show me on your fingers. How many places are you totally confident that you know what the value of the derivative is? If you're playing along on Zoom, you can type a number in the chat. How many points do you 100% know the slope? You can check in with the person next to you. See if they are thinking the same thing that you are. Take a chance. I see a brave 3 in the back. I see a brave 2 on Zoom. I got some 3s and some 2s in the room. Well, let me ask you this. Do you know what the slope is right here? Yeah, it's another 0. I'm going to go with there are actually only 2 places on the graph that on the portion of the graph I've shown where I am 100% confident I know what the slope is. The slope here is 0. But I can probably fake it and get close at a couple of other points as well. So I'm going to draw in some tangent lines here. So I got a tangent line over here. And I know that since sine like repeats itself, whatever the slope is over there should be the same as the slope over here. What do you think that looks like approximately as a slope? Cool. I'm going to go with, I have little dots on my paper. So that's like, at least how I've drawn it. That's like up to over 2. So 2 over 2 or a slope of 1. So I'm going to do the same thing over here. Now we didn't mention this, but sine has some symmetry to it, which means if we've called that a slope of 1, this slope over here is approximately -1. Now let's think about what's happening with the slopes in between. Well, if that's a slope of 1, and I pull some slopes in here that are like in between, the slopes are getting more and more shallow, but they're still positive values. On this side, my slopes are getting like more steep, but they're all negative values of slopes. In fact, these slopes down here are also negative. So maybe that's a slope of like, I don't know, -1/2. That's also a slope of -1/2. When I get over here, I'm into positive slopes again. So I'll call that like a slope of +1/2. And here's the magic. I didn't leave myself a lot of space, but I'm going to graph the derivative of sine of X. And I'm going to do it by graphing those slopes. But I'm going to do it, I don't know, really, really small because I didn't leave myself enough space. So I'm going to call this up here a slope of 1 because this axis now like is my slope. And this down here is a slope of -1. So when I started out, I'm at a slope of 1. I get to a slope of 0 over here. Right here, I'm at a slope of -1. Right here, I'm at a slope of 0. And right here, I'm back at a slope of +1. And you all are just going to have to give me some leeway. I'm going to magically connect those dots. And then someone is going to say, oh, hey, I recognize what that's a graph of. It is indeed a graph of cosine of X. That's our first trig derivative. We're going to start memorizing them all. The derivative of sine of X is cosine of X. Now, we can do that from the limit definition of the derivative, which your textbook does, but it's gross. And at the end of the day, we don't really need to know it. What we need to know is the end result. Derivative of sine of X is cosine of X. It's going to be something that we've just got to get memorized. I'm going to, oh, by the way, this picture, it's done better in your textbook. They didn't have to squish it in a little corner of the page. But it is in your textbook if anybody is wanting to like follow along with things to scale. Okay, I'm just gonna flip this and get some good stuff for your notes and loop back around to another quotient rule problem. So the derivative of sine of X, we just found is cosine of X. Now the cool thing is, just to be confusing, the derivative of cosine of X, maybe you know it from a previous life, maybe this is the first time you're seeing it, but the derivative of cosine of X is the negative of sine of X. And that happens because of how our slopes start out for cosine. And we could draw more pictures, but at the end of the day, we really just need to get these memorized. So what I want to do is to let y equal tangent of X and then find the derivative. And the way I'm going to do that is by remembering that tangent is actually equal to sine of X over cosine of X. So we're going to have a little quotient rule. So I'm going to give you all a couple minutes to use the quotient rule and these two facts about our derivatives to come up with a derivative for tangent of X. Put all the pieces where they go. And even if you know what the answer should be from the previous life, do it as a quotient rule right now just for practice. You can always check your answer from what you have somewhere in your memory if you have seen this stuff before. I do like colors. I like colors. I'm guessing we've got stuff that looks like garbage over garbage. And maybe we can play with the garbage together. So the derivative of sine of X would be cosine of X. So on top, I'm going to have cosine of X times another cosine of X minus, because we're doing quotient rule, we'll leave the sine of X alone and then times the derivative at the bottom, but that's going to be a negative sine of X. And that whole thing will be over cosine of X squared. We need to pause for a second to have a little notation break. And that notation break, maybe we already talked about this, maybe we didn't, I don't remember. Things are running together in my brain, but if I have cosine of x squared, notation-wise, we write that as cosine with a 2 and then the x. That's different from if I have cosine where the x squared is the argument or the angle of my cosine. This we would write as cosine with an x and a 2 at the end. It's subtle. It's super easy for your brain to grab the wrong one. It's always fine to use parentheses. But if you're not using parentheses, or in particular, if you're looking at a textbook problem, pay attention to where the number is to know whether it's an exponent on the x or really an exponent on the entire trig function. So if I rewrite this, cosine x times cosine x would be cosine squared, and we write that with a 2 here. Minus a minus is going to make that plus. Sine times sine, I can write as a sine with a 2 in front. And then in the bottom, I can also write that as cosine squared x. We didn't talk about this before, but the top of this is kind of the most fundamental trig identity. And if you only have one trig identity memorized, it ought to be that. Cosine squared plus sine squared of the same angle is equal to 1. And we can look at that on a unit circle momentarily. This, by the way, is not how the derivative of tangent is going to be written in any textbook or reference guide, because 1 over cosine is secretly secant. So this gets written as secant squared x. So in terms of adding to your list of stuff to memorize, the derivative of tangent of x is equal to secant squared x. I think I've got 2 minutes, so I do want to go back to like where that fundamental trig identity thing is coming from. So here's my unit circle, and I'm going to put a triangle on here. I'm going to call this theta and this side 1. So I'm just going to call these x and y for a second, but we already know that cosine of theta is equal to x and sine of theta is equal to y. But if I think about what Pythagorean theorem says here, x squared plus y squared has to be equal to 1, which would mean cosine squared theta plus sine squared theta would have to be equal to 1. Now, I think part of the thing that gets confusing between trig and then when we see it in calculus is in calculus, sometimes we use theta as the variable, but we often switch this out for x. Because theta was just a placeholder variable and x is just a placeholder variable. When we think about it like this, we're thinking about the x coordinate on a graph, and we're thinking about the y coordinate. And when we think about it like this, that x is some angle.